This is part 1 of a 3-part video. The title of this talk is Direct Numerical Simulation of Rough Wall Pipe. In this talk, we will look at the turbulent flow from the transitionally rough regime to the fully rough regime. Most surfaces are not smooth and contain some kind of roughness. In biological flows, roughness is observed in a stented artery, and how this foreign roughness affects blood flow is an area which is being thoroughly investigated. Another area where roughness is a problem is in the shipping industry. Here is a photo of a supertanker, and the surface of its hull is populated with biofouling. The photos on the right are some examples of calcareous fouling, where at the top we have tube worms and at the bottom we have barnacles. Roughness increases drag and subsequently increases the fuel consumption of the ship. It is estimated that this costs the global shipping industry tens of billions of dollars every year. This is a concern for countries like Australia and New Zealand, where due to its geographical location, relies heavily on sea transportation for international trade. The ultimate goal would be to create surfaces which can reduce drag. However, being able to accurately predict the drag penalty associated with a rough surface is equally important, as it allows engineers to make informed decisions. Now, I would like to talk about the methods which can be used to predict the drag of a rough surface. Here, we have a plot of the cost associated with the method used to predict drag against the accuracy of the method. At the down left corner of this plot, we have the Moody's diagram, which is basically a chart lookup method, and it is used in many engineering applications as it provides a quick estimate of the drag. However, it does not give a reliable drag prediction. At the other end of the spectrum, we can conduct scaled laboratory experiments which would give us very accurate drag predictions, but takes a lot of time and requires customized experimental setups. Direct numerical simulations, DNS, which is what we have done, can also be used to accurately predict the drag of a rough surface. DNS contains the time-resolved 3-dimensional flow field, which can be used to analyze the turbulent structures in the flow. However, in this talk, we will only be focusing on the mean statistics. One of the first few laboratory experiments conducted in a turbulent rough wall pipe was the work of Nicorazzi in 1933. The figure on the left shows his experimental setup, and the figure on the right is a photograph of his roughness, which consists of uniform sand grain. Here is a plot of his results, where the resistance factor is plotted against the bulk Reynolds number. He found that at low Reynolds numbers, when the flow is laminar, the resistance factor of the rough wall collapses onto the smooth wall and only depends on the bulk Reynolds number of the flow. Increasing the bulk Reynolds number, the flow then reaches the transitionally rough regime, where the resistance factor is a function of both the bulk Reynolds number and also the relative roughness of the pipe, which is the ratio of the height of the uniform sand grain roughness to the diameter of the pipe. Finally, the flow reaches the fully rough regime when the resistance factor depends only on the relative roughness of the pipe. Following the works of Nicorazzi, Colebrook then conducted turbulent rough wall experiments in commercial pipes, where the roughness elements are non-uniform. Results from his work is then used to create the Moody's diagram, which, as I've mentioned before, is commonly used in engineering applications. The y-axis of the Moody's diagram is the friction factor, which is synonymous to the resistance factor, and the x-axis is the bulk Reynolds number. Following in the spirit of Colebrook and Nicorazzi, we have simulated the turbulent rough wall flow in a pipe. The roughness consists of 3-dimensional sinusoids, which are governed by the following equation. R0 is the reference radius of the pipe, which is said to be the mean radius of the pipe. H is the roughness semi-amplitude, and lambda x and lambda s are the wavelengths of the roughness elements in the streamwise and spanwise directions. For all of the rough cases simulated, lambda x is equal to lambda s. DNS is conducted using CDP, which is an energy-conserving second-order finite volume code. A body-fitted mesh is used to grade the roughness elements, and it's ensured that all physical and time scales are fully resolved. Typically, in experiments, the flow changes from the transitionally rough regime to the fully rough regime by increasing the bulk velocity while maintaining a constant relative roughness. However, to simulate a turbulent flow at high Reynolds number is computationally very expensive. Therefore, what we have done is geometrically scale our roughness elements from the transitionally rough regime to the fully rough regime while maintaining a constant friction velocity. Here is a table of the parametric space where we have the roughness height on the left and the wavelength of the roughness elements on the top. The sketches shaded in grey are the cases which we have simulated at RETAL 180. These diagonal cases are the cases where we have geometrically scaled our roughness elements, and we will call these cases case S1. Here are the cases simulated at RETAL 540, and these cases are case S1. Now, I would like to look at the mean velocity profile for these cases. On the right hand side of this slide is the height and wavelength of the roughness elements and also the Reynolds number of the flow. At the bottom right corner of this plot, we have the blockage ratio of the pipe and also a sketch of the flow which has been simulated. This is the mean velocity profile for the smooth case simulated at RETAL 180, and you can see that the outer region of the flow does not collapse to the log law due to the low Reynolds number effect. This is the mean velocity profile for case h plus equals to 5, and the vertical dashed line demarcates the crest of the roughness elements. You can see that there is a downward shift in the mean velocity profile, and this is quantified by the roughness function, delta u plus. I can then plot the roughness function against the height of the roughness elements in the inset plot. Increasing the height of the roughness elements, you can see that there is an increase in the roughness function as you would expect. Now, when h plus equals to 20, the blockage ratio of the pipe is quite large, and therefore, if we want to simulate larger roughnesses, we would have to increase the Reynolds number of the flow. Here, we have simulated the flow at RETAL 540, and I have repeated case h plus equals to 20. There are slight differences in the roughness function obtained from the 180 and 540 simulations, and they are mostly due to the low Reynolds number effect of the smooth wall simulated at RETAL 180. Further increasing the height of the roughness elements, it appears that the flow reaches the fully rough regime when h plus is equals to 60. Comparing the roughness function of our sinusoidal surface in the fully rough regime with Nicorazzi's uniform sand grain roughness, we obtain an equivalent sand grain roughness height of 4.1. In the plot on the right, we have the roughness function plotted against the equivalent sand grain roughness height. You can see that our data lies below the data of both Nicorazzi and Colebrook. Fitting a fifth order curve fit to our data, it appears that our roughness function has an inflectional type behavior which is similar to that of Nicorazzi and does not follow the monotonic behavior of Colebrook. Now, we would like to look at wall drag. The pressure drop in the pipe is balanced by the wall shear stress, which is 100% viscous stress for a smooth wall. However, with roughness, the wall shear stress consists of both viscous stress and also pressure stress. Here is the contour of the time average streamwise pressure force normalized by the cell face area. You can see that the maximum pressure force occurs at the forward-facing part of the roughness elements. With increasing roughness height, we observe an increase in the pressure force. Here is the contour of the time average streamwise viscous force normalized by the cell face area. The maximum viscous force occurs at the crest of the roughness elements due to the large velocity gradients. With increasing roughness height, we observe a decrease in the viscous force. Now, we can then plot the pressure to viscous drag ratio against the roughness height. From this log-log plot, it appears that our data lies on a linear line fit. Plotting the pressure to total drag ratio, and now having a linear y-axis, you can see that our data still collapses quite well with the line fit. When the flow is in the fully rough regime, which is when h plus is approximately equal to 60, the pressure to total drag ratio is 0.75. This is close to the results obtained by Skaggs et al. In 1988, where they found the boundary between the transitionally and fully rough regime to occur when the pressure to total drag ratio is 0.6. They also found that the pressure to total drag ratio is larger than 0.8 in the fully rough regime for their particular roughness. On the other hand, Skeggs also found that the rough surface is hydraulically smooth when the pressure to total drag ratio is less than 0.1. From our line fit, this gives us a roughness height of approximately 0.4. Our roughness function curve fit, on the other hand, predicts a roughness height of 1.2, which is also a very small value. From the data which we have obtained from our numerical simulations, we are then able to create a virtual Modi's diagram. Here is a plot of the friction factor against the bulk Reynolds number. The bold dotted line is the friction factor for laminar flow, and the black solid line is the friction factor for turbulent smooth walls. You can see that our turbulent smooth wall simulations at RETA 180, 360 and 540 lies on top of this line. We can also plot our rough cases and plot lines of constant Re tau by equating the friction factor with the bulk Reynolds number. As expected, our data lies very close on these lines. Using Nickel's functional form and modifying it to include the effects of roughness, and using the roughness function curve fit which we have obtained earlier on, we can then calculate the bulk velocity of the rough wall, and subsequently plot lines of constant relative roughness. Here, I have a line of constant relative roughness where h over d is equal to 0.028, and here h over d is equals to 0.056. And our data lies reasonably well on these lines. So, from the numerical simulations which we have conducted, we were then able to create the virtual Modi's diagram, which is able to accurately predict the drag of this particular sinusoidal surface. Some of the work which I have presented here is published in the following paper. Thank you.